Salam, peace be upon you. My name is Muhammad Laik Siddiqui, the father of Holophase. You are deep in Book 9.2 of Episode 9, the Generative Grammar. Our climb through topological production has taken us to breathtaking vistas. We witnessed the first tear in smoothness, the birth of a defect, a stable knot in the phi-field. We discovered that such a knot is not anonymous. The very geometry of phi's cyclic values forces upon it an exact, immutable integer label, the winding number, a quantized charge written automatically by the universe's own grammar. Then we gave these labeled knots life, learning the rules of defect dynamics, how they move, attracted or repelled by the textured landscape of the phi-field itself, their continuous world lines through spacetime forbidding their random disappearance, mandating that births and deaths occur only in pairs. We have, in essence, created a cast of numbered characters and learned the basic verbs of their motion. But a story with characters who only move in straight lines is not yet a drama. Today, we witness the genesis of plot. Today, we discover what happens when these characters' paths entwine. In Braiding Productions, when Worldlines Weave Statistics, we will see that the simple act of defects weaving around one another in spacetime imprints a permanent global signature onto the state of the universe. A signature that dictates the deepest rules of identity and interaction, the very rules we call quantum statistics. Our anchor image is a master weaver at an ancient loom. Watch your hands. The vertical warp threads are taut, representing the unchanging flow of time. The horizontal weft thread, carried by the shuttle, represents the world line of a defect. As the shuttle passes, the weaver lifts some warp threads and lowers others, causing the weft to pass over and under in a specific sequence. This over and under is not random, it is a rule. Each pass of the shuttle, each crossing, changes the relationship between the threads. The emerging fabric bears the indelible memory of that crossing sequence. You cannot look at the finished cloth, its herringbone, its twill, its complex pattern, and pretend the crossings never happened. The pattern is the history of the weave. Today, we learn that the universe is such a loom. Space-time is the warp, defect word lines are the weft, and the statistical fabric of reality, why some things crowd together and others fiercely exclude, is the pattern woven by their braiding. Here is the distilled, beautiful puzzle of this part. We have established that there can be identical defects, same winding number, same properties. If we take two such identical defects and simply swap their positions in space, we end up with a configuration that is, by any local measurement, indistinguishable from the original. The characters have swapped chairs, but the stage looks the same. In a classical, common-sense world, swapping identical things leaves the world unchanged. Full stop. But our language is not classical at its root. It is built on phi, a cyclic phase. And indistinguishable for a phase on a circle does not necessarily mean numerically identical in every detail. It can mean the same up to an overall rotation of the entire phase field. Could the physical process of swapping, the actual journey of one defect around the other through time, itself perform such a global rotation? Could the braiding of word lines write a silent universal phase factor into the cosmic sentence? And if so, what profound consequences would that written phase have for how multiple defects are allowed to behave together? The answer is a resonant, inevitable yes. The consequences are the origin of the most fundamental classification in nature: boson versus fermion, the crowd lover versus the solitary exclusive. To understand this, we must think in 4 dimensions, in space-time. A swap is not an instantaneous teleportation. For defect A to take the place of defect B, their world lines, their histories, must travel around each other through time. In 3-dimensional space, to go around something, you must pass either to its left or its right, which from a top-down view looks like passing in front or behind. This crossing of world lines in spacetime creates a braid. And in topology, the pattern of a braid, which thread goes over which and in what sequence, is not a trivial detail. It is a robust, invariant property. It is a memory the system cannot erase without cutting the threads of history itself. Let us unfold this revelation with our triunity lens, observing how the act of braiding casts its 3 inseparable shadows across the dimensions of the story. The time echo of braiding, history as a physical record. The braid is, first and foremost, a chronological record. It encodes the sequence. Defect A moved around defect B in a clockwise loop, completing one full exchange. This temporal narrative becomes fossilized into the global state of the phi-field. Imagine two identical vortices in a fluid. You gently push one in a wide circle around the other until they have swapped places. You have performed one clockwise exchange. The fluid's flow pattern might eventually relax to look similar, but if the fluid has a memory, like a superfluid with a rigid phase field, the information about that circuit is stored. If you now reverse the process, moving the vortex counterclockwise back to its start, you are not just reversing time, you are unbraiding the world lines. The time echo of braiding is this profound principle. In a topological field, the history of exchanges is not forgotten. It becomes a physical, topological attribute of the present configuration. The system knows whether an even or odd number of swaps has occurred, even though the final snapshot of where the defects are looks identical. History matters because it is woven into the fabric. The space echo of braiding, the holonomy, a global phase shift. How does a space-time braid, a story of motion, leave a tangible mark on the spatial field right now? It does so through a concept called holonomy. For our ears, let's translate this as the whole path effect. As a defect's world line moves, it does not travel alone. It drags with it the local orientation, the phase, of the phi-field in its immediate neighborhood. Think of a spoon stirring honey. The spoon carries a little vortex of honey around with it. When you stir the spoon in a closed loop, you don't just move the honey near the spoon, you circulate the honey in the entire jar. The final orientation of a tiny flake suspended in the honey might be rotated from its starting point. This rotation depends only on the number of times you stirred the spoon around, not on how fast you stirred. Similarly, when one defect's word line braids around another, it effectively drags a loop of the phi-field's phase around its companion. The total phase accumulated by the phi-field, if you took a conceptual walk along a giant loop enclosing both defects after the braid, will be different than before the braid. This difference is a global phase shift. It is not a local change you can point to at a specific spot. It is a silent rotation of the entire background stage, a change in the global context of the field. The space echo of braiding is this intangible yet powerful topological phase, a signature written across the whole spatial domain determined solely by the braid pattern. The motion echo of braiding, the emergence of statistical behavior. This global phase shift is not a metaphysical curiosity. It translates directly into a forceful rule of motion and configuration for ensembles of identical defects. This is the moment statistics are born from geometry. Let's make it concrete with numbers our ears can hold. Suppose the braiding of two identical defects, one full swap, results in a global phase shift of +1. Multiplying by +1 changes nothing. The phi-field after the swap is numerically identical to the field before the swap. In this case, swapping truly leaves the world indistinguishable in every detail. Such defects are called bosons. They are supremely social. Their wave functions, their phi-field patterns, can overlap perfectly, reinforce each other, and an unlimited number of them can crowd into the same quantum state. This is Bose-Einstein condensation, the phenomenon of collective identity. Now, suppose the braiding results in a global phase shift of -1. Multiplying by -1 is equivalent, on a circle, to a rotation of 180 degrees. The field pattern is flipped in sign. If you now try to put two such defects into the exact same state to force their phi-field descriptions to be identical, you encounter a contradiction. Their fields, related by this negative sign, would try to cancel each other out where they overlap, forcing the total field to 0 at some point and violating its smoothness. The grammar forbids it. Therefore, such defects cannot occupy the same quantum state. They are called fermions. This is the Pauli exclusion principle, emerging not as an arbitrary law, but as a topological inevitability from the -1 phase written by their braid. Their motion and arrangements are fiercely constrained by this statistical rule. The motion echo of braiding is this statistical force, an effective, powerful constraint on how the word lines of many identical defects can collectively behave, derived entirely from the phase factor imprinted by their pairwise dances. Let us now locate this sublime discovery on the master tree. We are ascending to the Braiding Productions branch, the highest and most intricate limb growing from the topological production trunk. This branch depends utterly on the solidity of everything beneath it, on the existence of stable defects, on their possession of conserved integer labels, so identical has rigorous meaning, and on their having continuous, well-defined world lines that can be traced and intertwined. It enables the next monumental synthesis, the reconstruction of quantum theory's core as the natural dialect spoken by a topological holophase field. It demonstrates that the enigmatic rules of the quantum realm, superposition, interference, and above all, particle statistics, are not foreign axioms plastered onto reality, but are generated organically by the narrative grammar of phi. For now, we stand at the moment of genesis. Statistics are not imposed, they are woven. To ground this ethereal concept, let us light lanterns from across the scales of existence, scattering their illumination throughout our walk. A near lantern from the art of the craftsman, braiding leather or hair. Take 3 strips of leather. To create a simple braid, you cross the right strip over the middle, then the left strip over the new middle. This sequence, right over then left over, repeated, defines the braid. The crucial point is this. The final braid is a physical object whose structure encodes the entire history of those crossings. If you were to try and swap the positions of 2 adjacent strips within the braid without unbraiding, you would find it impossible. The braid pattern itself is the record of the swap. Furthermore, if the leather had a grain or a die pattern that was sensitive to twist, the act of crossing one strip over another might introduce a permanent half-twist in the grains, changing the overall reflective property of the braid. The final state depends on the braiding history. A middle lantern, from Computer Science and Puzzles. The tangled cords behind the desk. You have 2 identical black USB cables plugged into a hub. They are tangled. To swap which port each is plugged into, you must untangle them. This untangling process involves a series of maneuvers where one cable loop is passed through another. The final, functional configuration, cable A in port 1, cable B in port 2, might be indistinguishable from the starting one after a swap. But the path to get there, the sequence of loops and passes, is a braid. If the cables were carrying high-frequency data signals, the specific braiding path might affect signal integrity due to induced crosstalk or impedance changes. The physical outcome is subtly shaped by the topology of the rearrangement, not just its final state. A far lantern from the forefront of condensed matter physics. Anyons in 2-dimensional electron systems. This is the direct, magnificent, experimental validation of the braiding principle. In certain 2-dimensional materials, under intense magnetic fields, like those exhibiting the fractional quantum Hall effect, the collective excitations behave as particles confined to a plane. In 2 dimensions, a path cannot go over another, it must go around. This restriction enriches the possible braiding patterns. When 2 of these identical quasi-particles are swapped, the resulting phase shift is not limited to +1 or -1. It can be any phase on the circle, 120 degrees, 90 degrees, any complex number of magnitude 1. Hence, they are named anyons. This phase is not theoretical, it is measured. In pioneering experiments, physicists use nanofabricated electrodes to create, trap, and literally braid these quasi-particles around one another along precise paths. They then measure interference patterns in the electrical conductance. The results show discrete jumps that depend solely on the number and direction of the braiding operations. A single swap yields a specific, measurable phase shift. A double swap yields the square of that phase. The data matches the predictions of topological braiding theory with stunning precision. Here, in a lab on Earth, we see Worldlines weaving statistics and the woven pattern dictating hard, numerical experimental outcomes. From the leather braid to the tangled cable to the quantum Hall quasi-particle, a universal theme resonates. The history of how paths intertwine becomes a permanent topological feature that can actively constrain or define the state and observable behavior of a system. The weave is not just decoration, it is data. What, therefore, is the specific grammatical role of braiding productions within the Holophase language? It is the syntactic rule for the exchange of identical terms. It is the part of the universal grammar that answers the meta-question. What is the transformation rule applied to a sentence when 2 identical lexical items within it swap their positions? In everyday language, swapping dog and cat in "the dog chased the cat" creates a new meaning. But in the physics of fundamental entities, swapping identical particles should yield a sentence with the same observable meaning. Braiding production is the rule that declares Swapping identical terms is a grammatically valid operation, but it may obligatorily induce a global phase transformation, a silent punctuation mark on the entire sentence, that subsequently governs how other sentences, like those about occupation, can be grammatically constructed. It is the rule that translates kinematic geometry into statistical syntax. The core question this part poses to phi is, what is the invariant, global consequence of transporting identical topological defects around one another in spacetime? And how does that consequent invariant constrain the permissible multi-defect states that the field can physically express? We have graduated from analyzing single defects and their pair interactions to decoding the collective grammar of ensembles. What does this braiding production rule actively do within the generative engine? It classifies the universe's identical actors into distinct statistical families: bosonic, fermionic, and ionic. It enforces high-level laws of congregation and exclusion, Pauli principle, condensation, as direct, low-level topological constraints, preventing grammatical nonsense. It generates quintessentially quantum mechanical behavior, complex amplitude interference and superposition, from the classical seeming concept of continuous world lines. It provides a geometric and topological origin for the phase factors that are the essential currency of quantum theory, rooting them in the memory of paths. Now we must consider stability and breakdown. The rule that braiding determines statistics is a topological invariant. It holds rigorously under these conditions. The defects must be truly identical, same topological charge. Their word lines must remain well separated during the braiding process, so the exchange is adiabatic or clean, and the dimensionality of the space they move in must be accounted for, with two spatial dimensions offering the richest braid group and thus the possibility of anionic statistics. The rule breaks down or becomes ambiguous if the defects are not identical, if the braiding is messy, involving close approaches that trigger non-topological interactions, or if we attempt to apply the simple three-dimensional picture to a context where other dominant topological effects obscure the braid group structure. Within its proper domain, the clean adiabatic braiding of identical topological defects, the statistical phase is as robust and unchangeable as the knot in a tightly pulled string. This brings us, as always, to the heart of our discipline, falsifiability. The grand claim that particle statistics emerge from the topological braiding of defect world lines in the Holophase field is majestic in scope, but it must remain tethered to the earth of testable prediction. The central claim. In a physical system accurately described by a circle-valued phi-field, whose dominant excitations are topological defects, the result of exchanging two identical defects will be fully determined by the topological equivalence class of the spacetime braid. This means the outcome, the global phase factor, depends only on the number of times one defect wound around the other and the direction, not on the speed, the precise contour of the path, or other microscopic details. A critical, testable consequence is that performing the exchange operation twice, a full 360-degree rotation of one defect around the other, must yield a phase factor that is the square of the phase from a single exchange. For bosons, +1 squared equals +1. For fermions, -1 squared equals +1. In both these familiar cases, two exchanges returns the system to a state indistinguishable from the original. For anyons, with a single exchange phase of, say, e to the power of I times theta, the double exchange phase would be e to the power of I times 2 theta, a distinct and predictable result. A concrete modern measurement scene. Let's return to the arena of two-dimensional electron gases in the fractional quantum Hall regime, our most potent laboratory. Experimenters begin with a semiconductor chip chilled to near absolute zero and subjected to a powerful magnetic field. At specific magnetic field strengths, the electron fluid condenses into a topological quantum liquid. Using electron beam lithography, they etch tiny gates on the surface of the chip. By applying precise voltage pulses to these gates, they can create, move, and braid the emergent quasiparticles, which are defects in this quantum fluid. They design an interferometer on the chip, a path along which a test quasiparticle can travel, splitting into two arms that encircle a central region. Inside this central region, they place and then braid other quasiparticles. The act of braiding changes the topological sector of the region, which in turn affects the phase accumulated by the test quasiparticle as it encircles the area. This phase shift is read out as a change in the interference pattern, visible in the electrical conductance of the device. They perform a meticulous sequence. measure the baseline interference pattern, perform a controlled braid of one quasi-particle around another inside the loop, then measure the pattern again. The pass condition, validation of the theory. The interference signal shows sharp, discrete jumps between a small set of stable values. These jumps correlate perfectly with the completion of elementary braiding operations. For example, one clockwise exchange, one counterclockwise exchange, a double exchange. Crucially, the new interference pattern remains stable against small variations in gate voltages. It is locked in by topology. The phase shift from a double exchange is measured to be the square of the phase shift from a single exchange, confirming the group structure of the braid operations. The data from hundreds of runs clusters around these predicted discrete outcomes, with errors due only to instrumental noise and residual thermal fluctuations. The braiding of worldlines directly and predictably weaves a measurable statistical phase. The fail condition, falsification of the theory. The interference signal varies continuously and sensitively, with tiny adjustments to the gate voltages used to perform the braid, indicating the outcome depends on microscopic path details, not just topology. Or, after performing what is topologically a clear full exchange, the system fails to settle into a predictable new interference state. Most decisively, if in a system designed to host, for example, fermionic excitations, a double exchange operation does not return the interference pattern to its original state, the core premise that statistics derive from the topology of worldline braiding would be shattered. It would force a fundamental reconsideration, suggesting that particle identity and exchange rules are governed by principles deeper or altogether different from the braiding of lines in the holophase field. This rigorous falsifiability is our compass. It ensures that this profound architectural idea remains in honest dialogue with the empirical world, vulnerable to being proven incomplete or wrong by a clear experiment. Let us now cultivate a practical recognition skill. You can train your intuition to perceive the logic of braiding productions in diverse scenarios where the sequence of operations or the intertwining of histories alters the final outcome, even when the beginning and end states appear superficially identical. Observe the shuffling of a deck of cards. Take two identical decks, both brand new and arranged in the same factory order. Have two people shuffle them. Even if they both perform the same number of shuffles, the specific sequence of card crossings, the braiding of the card stack, will be different in each case. The final order of the two decks will be different, even though they started identical and underwent the same amount of shuffling. The history of the weave, the shuffle, determines the present state. If the cards were sensitive, for example marked by bending, the specific braid would leave a unique physical imprint. Consider protocols in diplomacy or business negotiations. Two identical proposals might be presented to two identical parties. However, the order in which side agreements are reached, the sequence of bilateral meetings, which is a braiding of communication channels, can lead to radically different final coalition structures or deal terms. The braid of interactions weaves the social outcome. Analyze the flight paths of aircraft in a holding pattern around an airport. Two identical planes awaiting landing clearance might be instructed to orbit in stacked loops. Their paths in the sky, viewed over time, braid around each other. A controller's decision to have plane A cross in front of plane B's path versus behind it creates a different topological history in the airspace, with implications for collision avoidance systems and scheduling. The safe resolution is dependent on the controlled braiding of their trajectories. Whenever you encounter a situation where exchanging or rearranging identical elements involves a process whose specific pathway leaves a lasting imprint on the global structure of the system, you are witnessing a conceptual relative of braiding productions. You are seeing that history, encoded in topology, can govern present possibilities. We must now connect this discovery inextricably to our journey through the holophase language. In the previous part, dynamics provided the verbs for our numbered nouns. Here, braiding provides the foundational rules of syntax for sentences containing multiple identical nouns. We have not postulated a strange quantum rule. We have simply pursued the logical end of our framework. We took our topological defects, already endowed with conserved labels and governed by field-derived dynamics, and asked the natural question about what happens when their spacetime threads intertwine. The resulting global phase factors are the first genuinely quantum phenomena to emerge seamlessly from our underlying continuous field narrative. This is the profound power of topology. Global, holistic constraints can produce effects that appear mysterious, non-local, and discrete from a purely local mechanical perspective. If you want to see the full mathematical derivations and exact equations behind this idea, the formal definition of the braid group, the computation of unitary representations that give the phase factors, the detailed connection to Berry phase and holonomy, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and feel the significance of our vantage point within episode 9. In book 9.2, Topological Production, we have now reached a soaring peak. Our ascent began with the genesis of persistent entities, defects. We then saw them receive their immutable names, winding numbers. We learned the principles of their motion, dynamics from conservation and gradient. And now, we have uncovered the profound rules that govern their collective identity when they dance together, braiding and statistics. We have derived from the geometry and continuity of a single fundamental field the very principle that bifurcates the material world into two great families, the congregators and the exclusives. This is not a minor result. It is a demonstration that the Holophase language possesses the generative depth to produce the architectural bedrock of quantum physics from a coherent topological grammar. In the next part, we will descend from this peak of knots and weaves and return to the open, waving fields of smooth phi. We will cross the threshold into waves and fields. Here, we will explore how phi composes ripples and paragraphs, how simple oscillatory sentences are formed, governed by rules called dispersion relations that link time frequency, omega, to spatial frequency, k. We will see how localized wave packets, the carriers of information and energy, propagate and disperse. And we will witness how overlapping waves can interfere, creating patterns of light and dark, or lock in step to form coherent fields that act as one. The language will show us how the smooth, undulatory face of reality is generated, complementing the particulate, defect-based face we have just come to understand. Before we conclude, the mandatory zoom out to hold our scope. Every concept we have traversed, from defect creation to winding number assignment, from defect dynamics to braiding statistics, remains nothing more than phi and the inexorable consequences of its structure. We have added no new substances, no new metaphysical layers. We have only deepened our reading of the grammar, learning to parse more complex sentences. One field, phi, plus its infinite tower of derivative questions. In this episode, we have journeyed from the first sentence through the engine of smooth production into the realm of topological production, where we learn to write stable things, label them, animate them, and now to understand the profound syntactic rules that emerge when their stories intertwine. The generative power of this single language continues to unfold, revealing a universe where the deepest quantum mysteries are native, born of ancient geometric and topological truths. As we conclude, hold firmly the image of the master weaver at her loom. The vertical warp is the relentless flow of time. Each horizontal pass of the shuttle is the world line of a defect, laid down across history. The act of raising and lowering specific warp threads, the decision of over and under, is the braiding production rule, dictated by the interactions of the field. The slowly emerging fabric is the universe itself. Its grand pattern reveals everything. Here, a smooth, uniform stretch where bosonic threads lie perfectly parallel, condensing into a superfluid sheet. There, a tight, checkered weave where fermionic threads strictly avoid occupying the same square, creating the solid structure of matter. And in specialized corners, intricate, fractional braids where anionic threads intertwine in patterns that hold the promise of topological quantum computation. The universe does not obey statistical laws. It is the statistical fabric, woven thread by thread, braid by braid, in the endless loom of spacetime. The rules of identity are the indelible grammar of the weave. Salam, and peace be upon you.